Welcome to our session on superconductivity in Majorana physics. In this Jupyter notebook, we are going to compute several models that show superconductivity, both conventional, unconventional superconductivity, and also Majorana excitations. And in particular, we are going to see how superconductivity arises from attractive interactions and how the structure of the superconducting order determines the properties of the superconductor. So let us start with the first exercises, and we are going to start first with a reminder about the Nambu electronic structure in the absence of superconductivity. So the whole idea is that when you have a superconducting state, in order to understand the excitations, you need to enlarge the the state itself. So instead of working just with electrons, you need to work with electrons and holes. And this is what we call a Nambu spinor. And this is what we are going to do here in practice. So we start with a square lattice. We generate the Hamiltonian at a certain filling. And what we are going to do is we are going to plot the electronic structure without superconductivity, meaning without the Nambu basis, in the presence of the Nambu basis. And we are going to project the band structure in the Nambu basis onto the electron sector. So these are the different code that you see here. And so this is what you observe here, and we can execute it so that you see the result. So what you see is that originally our band structure of the square lattice is this one. So it's a cosine-like dispersion. When we add the Nambu spinor, then we get our original electron dispersion and then the whole replica. And this is just this fictitious replica that appears because of the Bogoliubov-de Hamiltonian. And then, of course, once we project back our Hamiltonian onto the original electronic states, we recover the electron spectral function that reflects the original band structure. Okay, and so the question is discuss how the bands with a Nambu spinor can be understood in terms of the bands without a Nambu spinor. And so that's what we mentioned before. In short, the red band is our original electron. The blue band is our whole replica that comes from the Nambu spinor. So let us move on now to include superconductivity in the previous electronic structure. So we have a very similar code. We create a square lattice. We first plot the bands without superconductivity. Then we add superconductivity, that is this statement that you see there, and we compute the band structure projected onto the electronic sector. And then furthermore, we just plot the electron part of the band structure. So we execute the code, and what you observe is the plot that will appear shortly. So this is the original band, that it's again our cosine-like dispersion. And in the presence of superconductivity, now you see that there's an anti-crossing between the electron and hole bands. And this anti-crossing that you see over there is controlled by delta. And when you project back these states onto the electronic states, what you see is that the electronic states also got a gap, which is effectively just the red part of the band structure that you see here. And so this gap is the superconducting gap. And so the first question is to change the value of the superconducting order and see what happens. So, okay, what we have to do is to change here the value of the superconducting order. So let's try, for example, something like 0.2. And when you use 0.2, you see that the gap actually becomes smaller, right? So this S-wave gap precisely controls what is the value of the anti-crossing between the electron bands and the hole bands. And of course, if you make it bigger, so let's say that you make it equal to 2, which is a very large value, you see that the anti-crossing is way bigger. And then the next question is discuss why the gap opens when you add superconductivity. And so the reason is that the gap enters as an off-diagonal element in the Bogoliubov-de Hamiltonian. And when you have this off-diagonal element, you create anti-crossings between the electron bands and the hole bands at all zero energies. Okay, let's continue with the next question, which is about superconductivity, the full spectral function, and the electron spectral function. And so what we are going to do here is to look at the relationship between the Nambu spinor band structure, the full Bogoliubov-de spectral function, and the electron spectral function. So what we are going to do is we are going to take the geometry of a one-dimensional chain, generate the Hamiltonian, set a certain filling, add superconductivity, and then after adding superconductivity, we are going to compute the band structure projected onto the electron sector. And apart from the band structure, we are going to compute the total density of states and the density of states projected onto the electron part. And so let us execute this. and see what we get. So this is the Bogoliubov-de Gennes band structure. So we have a original band structure that has an anti-crossing due to the superconductivity. The total density of states is the density of states of this full band structure. So you get non-zero values both in the red bands and non-zero values in the blue bands. And then the electron density of states is just the projection of the Bogoliubov-de Gennes electronic structure onto the true electronic states. And so the first question is, why are the full Bogoliubov-de Gennes density of states and the electron density of states different? The reason is that the Bogoliubov-de Gennes density of states reflects both the electron and the whole part. And remember that the whole part is just a mathematical replica of the electron part, whereas the electron density of states just reflects the true electron spectral function. So the electron dose is the experimentally observable one. Now, the next question is, change the filling of the system. How does the density of density of states change? So to change the filling, we can just go to this line here where we have the filling, right? So we can take, for example, half filling. And if we take half filling, what we actually get is that, of course, the total density of states has changed now. But the important thing is that a gap remains. A gap remains both in the total density of states and in the electronic density of states. And of course, if we take a different filling, so a much smaller one, we see that the gap also remains both in the total density of states and the electron density of states. And of course, the electron density of states and total density of states are different. And then the last question, remove superconductivity. How does the density of states look like? And which one is the experimental observable? So if we want to remove the superconductivity, we can just change this value here, right? So, or put it to a very small value, so something like 10 to the minus 7. And so when we do this, we observe the following. So this is our Bogoliubov-de Gennes band structure. Now there's no anti-crossing because the superconductivity is very, very small. The total density of states reflects both bands, but the real density of states only reflects one of them, which is the red one. And of course, the observable one is this one. So here we have a system that has a very small filling, and therefore the real accessible states are the ones reflected by the electron density of states. Let us move on with the next case, which is the impact of superconductivity in an electronic structure. So we are going to see how the superconducting order affects an electronic structure. And for that, we are going to change the chemical potential of a lattice and see how the electronic structure changes with the chemical potential. And so what we are going to do is we are going to take a honeycomb lattice, and we are going to put different fillings in the honeycomb lattice that they are going to be controlled by a chemical potential. So for each different chemical potential, we generate the Hamiltonian, we add the chemical potential, we add S-wave superconductivity, and then we compute the bands and we plot the bands, and the bands are projected onto the electron sector. So the parts of the band structure that you are going to see are already the physically relevant ones that are the electron part of the projection. And so this is the result that you see for different chemical potentials, right? So the band structure changes as a function of the chemical potential, but what is important is that a gap always appears. And of course, this gap is the superconducting gap. So let us go through a question. So first, switch off the superconducting order. Do you still see a gap at the different chemical potentials? Okay, so if we want to switch off the superconducting order, we can just put it to 0 here, right? And recompute and see the result that we get. So now, if we have 0 superconducting order, what you actually see is that shifting the chemical potential just rigidly shifts all the bands. So nothing special happens. Your system is a metal all the time. The system always has states at the Fermi energy and no gap appears. Now, next question. Does the gap depend on the chemical potential for finite superconducting order? So for this, we can just add a finite superconducting order. Let it just say 0.3 and see what happens. And so what you actually observe is that when we put the superconducting gap equal to 0.3, we get all the time a gap of 0.3 in the electronic structure. And this is, of course, by definition. So the parameter that appears in the Bogoliubov-de Gennes Hamiltonian is precisely the value of the gap. And it does not depend how your electronic structure is. The gap is always delta. And so that's what you effectively see here, regardless of whether your chemical potential is close to this crossing or away from this crossing, the value of the anti-crossing is always the same. And then the last question is to replace the honeycomb lattice, but by any other type of lattice, and whether we see a gap opening for different chemical potentials. And so what we can do is to replace the honeycomb lattice, for example, by a triangular lattice. And so when we replace it by a triangular lattice, you see that even though the electronic structure is definitely different, the existence of a gap remains. And the gap is, of course, all the time the same for all the chemical potentials. Okay, let's continue with the next case, which is an S-wave superconducting state driven by attractive interactions. So far, we have added superconductivity by hand in the Hamiltonian, meaning that we were starting with the result of a mean field calculation. Now, what we are going to do is we are going to do this mean field calculation. So the whole idea is that we are going to take a Hamiltonian for a one-dimensional chain, set up the Nambu spinor, and then do a self-consistent calculation with attractive interactions. So this is the line here that you see, get mean field Hamiltonian. And so we can do the self-consistent calculation with u equal to minus 1.0 at a certain filling. And then what we do is we plot the band structure without interactions and after doing the mean field interaction, the mean field calculation. And so this is what we are going to do right now. So without interactions, the electronic structure that we get is something like this. So we have the bands of a one-dimensional chain at a very low filling, and then once we add interactions, the band structure that we get is this one. So you see that we get the same types of anti-crossings that we were expecting from a superconducting state, but now we are not putting superconductivity by so is driven by attractive interactions. And this is, of course, the realistic case. So superconductivity is always going to appear due to the attractive interactions. And so we now answer this question. So first, to identify the gap that appears due to interaction. So the gap is precisely this one. So this is the superconducting gap. And since we are putting local interactions, local attractive interactions, then we know that the nature of the superconducting gap is S-wave. So here we have an S-wave singlet state that is driven by interactions. And then the next question is to increase the value of the attractive interaction. What happens to the superconducting gap? Okay, so what we can do is we can just copy the whole cell and put it below so that we can compare the plots. And we are going to take an interaction of, for example, 0.3 and see what is the result that we get. And so now you see that without interactions, we get the same result as before, but now with interactions, we get a much bigger gap. So the bigger the interaction, the bigger the value of the gap that we get after doing the self-consistency. But something that is very important with superconductivity is that no matter how small your attractive interaction is, you will always get a finite value of the superconducting gap. Okay, so now let's look at the dependence on the strength of the attractive interaction. So the whole idea is that we are going to perform calculations at different values of the interaction and see that at all these values we are going to get a superconducting state. And so we take a one-dimensional chain, we generate our Hamiltonian, we set up the Nambu spinor, and now we are going to do self-consistent mean field calculations for different values of the interaction. So we are going to take in particular -1, -1.5, and -2, all at filling 0.1. We'll compute the bands and plot the bands. Okay, and so if we do this, we get the following plot. So the idea is that as we make the interaction stronger, the gap becomes bigger. And so let's look at the question. So perform the self-consistent calculation above, including an external Zeeman field that the superconducting gap become bigger or smaller. And this effect is called paramagnetic depairing. So if we want to add a Zeeman field, what we have to do is to add just an exchange coupling, which is this line that you see here. So we are going to add small external field, okay, so 0.5, and see how the plot looks like. And so when we add the Zeeman field, Zeeman itself competes with the superconducting state. And in particular, you see that for this Zeeman field of 0.5, we completely destroyed the superconducting state, right? So no matter how strong our attractive interactions are, we don't have superconductivity. If we start adding a smaller Zeeman field, and in particular a Zeeman field that starts competing with a superconducting state, then you see that you may still get superconductivity. So at this value of u, you still get a gapless state, right? Although you see that there are some signs that superconductivity wants to appear. And of course, as you make the interaction more attractive, so more strong from an attractive point of view, then you eventually end up in a full superconducting state. And so, of course, an external magnetic field, in particular an external Zeeman field, quenches a superconducting state. And this is precisely what you see here. And so if your superconducting gap is not strong enough, then the Zeeman field is going to quench the superconducting state. If your superconducting gap is very strong, then it will survive this Zeeman field. And this is, of course, something that happens for spin singlet superconductors. Spin triplet superconductors, they can actually survive this impling magnetic field much more than singlets. And so now let us look at different types of unconventional singlet superconducting orders. Before we were considering just S-wave superconductors, but of course there are more complex spin singlet superconductors. And so these are the symmetries that you see here. So we can run them to generate them on the fly. So the whole idea is that this plot is the momentum dependence of the superconducting order, meaning that your superconducting order is a function of k, where k is the momentum space wave vector, and different superconducting orders have different dependencies of this wave vector k. In particular, the S-wave pairing has no dependence whatsoever, so it's completely flat in momentum space. The dx squared minus y squared pairing has a dependence that looks like this, so it's positive here, then negative, then positive, then negative. So the sign changes, let's say once here, once there, once there, and once there, as you wind around the gamma point. And of course, one can have orders that are still S-wave, and they are still singlets, but where the sign of the gap changes. And this is called the extended S-wave pairing. So here it is all the time positive, but then if you go to other momenta, it is negative. So let us look at the question now. So first, we have to discuss what you can see from the plots above, and that how do we know that all these pairing symmetries are singlet. And so the whole idea is that in superconductors, we can have spin singlet and we can have spin triplet, right? If we have spin singlet, then the superconducting order parameter needs to be even in momentum space. And if we have triplet, it needs to be odd in momentum space. So a S-wave pairing, it's even in momentum space in a trivial way, right? Because it has the same sign everywhere. This superconducting order is also even in momentum space, right? Because if you go from plus k to minus k, you always get that the color is the same. So here is red, and at minus k is also red. And if you start in this loop, then minus k is also blue. And the same applies for extended S-wave. So in practice, to know if you have an singlet superconducting order, you just need to check if the superconducting order is even, meaning that when you go from plus k to minus k, the sign of the gap does not change. And then we have another question. So does the extended S-wave order lead to a fully gapped superconductor? And so this is a question that depends very strongly on the Fermi surface. If you happen to have a Fermi surface that it's right here around the gamma point, then of course you pick up all the time a gap that is non-zero and that it's positive. But if your Fermi surface happens to cross these white regions, then your superconducting order would be non-zero, would be zero at certain points of the Fermi surface, and therefore at those points of the Fermi surface, you would not open a gap. So extended S-wave superconductors can have a gap, or they can be gapless, and this depends very strongly on how your Fermi surface is. Okay, so let's move on to the next questions about the impact of spin splitting in the electronic structure. So we first will see how the spin splitting works in an electronic structure. So what we are going to take is we take a one-dimensional chain, we generate the Hamiltonian, and we compute the bands. And now we add an exchange coupling and we compute the bands again. So if we do this, what we actually get is that the band structure looks like this. So the band structure without an exchange coupling has a single band, and then when we add the two bands, then we get one band for spin up and another band for spin down. Okay, so first of all, we need to change the value of the exchange coupling in the Hamiltonian and see what happens to the splitting between up and down spins. So if we take a bigger splitting, then the splitting between the bands becomes bigger, right? So the value of the exchange coupling is effectively the splitting between these bands. And then the next question is if the band structure breaks down reversal symmetry, and how do we see that? Well, and so the point is that if up electrons have a different energy than down electrons, in the whole Bernoulli zone, then we break time reversal symmetry, because you can think that you will have more up electrons than down electrons in this system. Okay, so now let us move on to study a spin triplet superconductor and show that it has edge modes. So the way in which we are going to build a spin triplet superconductor is by adding a pairing that is a p wave pairing, okay? And so this is what we had with a pairing mode p wave with a certain value of delta and with a certain d vector. And please recall that the d vector was this vector that allows you to define in which order the triplet is oriented. So the triplet order parameter behaves in a certain way like a magnetization, and so it has a directionality. And so what we do is we generate a chain, we generate the Hamiltonian of this triplet chain, we compute the band structure, and then we do the same, but now for a finite system. So we take a large finite system, we add the superconducting order in this large finite system, and we compute the bands. And when we do that, we get the following. So the two-dimensional electronic structure looks like this. So this is the electron band, and this is the hole band. And of course, this anti-crossing is the superconducting order. But now, when we look at a finite system, we see that in a finite system, we have a set of states over here, another set of states over there, but then there are zero modes over here. And so these zero modes are precisely topological zero modes, and they are Majorana excitations. And the bottom line is that a one-dimensional p-wave superconductor is a topological superconductor that shows Majorana modes. Okay, so the first question is to change the value of the superconducting order delta and see how the electronic structure changes. So the idea is that if we change the value of delta, then the value of the gap changes, of course. So the bigger the delta, the bigger this anti-crossing, but this phenomenology of having zero modes is robust as long as the system is large enough. Then the next question is, why are there zero modes for a finite system but not for an infinite system? And this is precisely this topological nature that we discussed before. This topological gap that you see in the superconductor is associated with the emergence of Majorana modes, which are the topological modes associated with this gap. So in practice, if you have a system that is infinite, there are no edges, so topological modes do not appear. But once you have a system that is finite, then you have edge modes, and these edge modes appear right at the edge. So these modes that you see here in zero, they appear because your system is topological and it's finite. And then the next question is to decrease the length of the finite system and see what happens to the zero modes. And so the idea is that the zero modes will appear at zero energy if the system is large enough. But if your system is not large enough, you see that you don't get a clear zero mode. And the reason for this is because the modes in the two edges, they hybridize. So only when the system is large enough, you get a zero mode that is robust and that appears exactly at zero energy. But if your system is finite, then the two modes that appear on the edges are going to hybridize and will appear at finite energy. Okay, so let us look a bit more into Majorana modes in spin triplet superconductor. So now we are going to analyze more in detail the topological modes. So for that, we are going to again generate our one-dimensional topological model. So this is going to be this one-dimensional chain with p-wave superconductivity. And we are going to take a relatively large one-dimensional chain with edges, and we are going to add superconductivity to this system. And once we have our Hamiltonian, we are going to compute the density of states in different places. We are going to compute the density of state in the first site, in the bulk, let's say close to the edge, and then in the bulk. So the first one is the first site, then the next one is close to the edge, but not exactly on the edge, and then in the bulk. And so let us compute this and see what we get. So if we look at the density of states right at the edge, so what you see is a peak at zero energy, right? This is the zero energy mode that we were discussing before. Then you start going towards the bulk, and you see that the amplitude of your zero energy peak decreases. This means that the amplitude of your zero mode wave function becomes smaller as you go towards the bulk. And then once you are exactly in the bulk, your zero mode disappeared and you just have your bulk states. And so now the question is to decrease the length L of the finite chain and see what happens. And so now the idea is that we are going to take a chain that is shorter. So let's take something with 20 sites, for example. And when you take something with 20 sites, you see that at the edge, you still get a peak at zero energy. But then as you go towards the bulk, you remain, the zero energy peak remains. So what this actually means is that the mode is not completely isolated in the edge, but it's also leaking a little bit in the bulk. And of course, if it leaks to the bulk, then both edges are effectively coupled. Okay, so now let us move on to consider the emergence of Majorana modes as a function of the size of the superconductor. So we are going to use the same model as before. So we are going to take a one-dimensional chain with p-wave superconductivity. And what we are going to do is we are going to compute the system at different lengths. So these are the lengths that we are going to consider. So from 4 to 42 and steps of 2. And for each different length, we are going to add certain superconducting order, a certain chemical potential. We generate our Hamiltonian, and then we compute the density of states at the edge and in the bulk. And what we do at the end is we plot all the density of states at the edge for the different system sizes and all the density of states in the bulk for all the different system sizes. And that's the plot that we are going to analyze. Okay, so the x-axis is the length, the y-axis is the energy. And so what you see is that as you make the system bigger and bigger and bigger, then the density of states at the edge slowly becomes a zero energy mode. So at the beginning, you have some mode at finite energy, but eventually, as your system is big enough, then it gets spinned at zero energy. But then in the bulk, as you make the system bigger and bigger, you start seeing some peak close to zero energy. That was the original edge mode. But then once the system is big enough, then you no longer see the edge mode. Okay, so let us go through the question. So the first one is, why do the zero modes appear in the edge as the system gets bigger? So the reason for this is because these modes are topological modes. These are the Majorana bounded states of a p-wave superconductor, of a one-dimensional topological superconductor. And so when the system is very big, the two edges are decoupled and the modes get pinned at zero energy as given by the electron hole symmetry of the Hamiltonian. Next question is, why do the zero modes disappear from the bulk as the system gets bigger? Well, the reason is that when the bulk is big enough, then the edges are far enough from the center of the system, and so you don't see the zero modes anymore. And of course, the bulk has a full gap. Then the next question asks us to increase the value of the topological superconducting gap delta and see what happens and why. And so this is something that we can do here by changing the value of delta. And so it can be actually convenient to do it in a different cell so that we can compare the two results. So we are going to take a superconducting gap of, for example, 0.3, that is bigger than the one that is considered above. And so now what you see is that with this superconducting gap, you get a flat band very quickly. And I mean, this is of course not a flat band, but a zero mode very quickly, even for small lengths. And of course, in the bulk of the system, the mode close to zero energy disappears very quickly because your gap is so big that you enter in the bulk regime very quickly. And so the opposite will happen if we decrease the value of the gap, right? So if you decrease the value of the topological gap, then you will see that your edge modes remain still oscillate for relatively large system sizes, and the bulk density of states still sees a little bit of the edge mode even for relatively big system sizes. Okay, and then the last question is to change the chemical potential mu and see what happens and why. And so what we are going to do is we are going to take the same delta before, so 0.1, and the chemical potential that we are going to take is now different. So we'll take superconductivity 0.1, and now as chemical potential, let us take something like 0.5. And so the idea is that as you change the chemical potential, then the way in which your edge modes go towards zero as you increase the length changes. So here you see that they move in this way, whereas for the other chemical potential, they were like this. But what's important is that when the system is big enough, then your modes get pinned at zero energy at the edge, and in the bulk, nothing remains. So in practice, when the system is big enough, no matter what your chemical potential is, with a p-wave superconductor, then you will get your topological modes. And the reason is because the topology is enforced by the nature of the superconducting order. Okay, so before we were putting the p-wave superconducting order by hand in the Hamiltonian, so we were assuming that there was a external p-wave order. This p-wave order, of course, it can appear due to many body interactions, and that's what we are going to do now. So we are going to see how an interacting Hamiltonian can actually give rise to a p-wave superconducting order. So we are going to take a triangular lattice. We are going to put a certain exchange coupling, so -2. This is to make the system magnetic. So when we make a system magnetic, we are in a way quenching the appearance of a singlet superconducting order so that the only remaining order is the p-wave order. And so the whole idea is that we are going to do a mean field calculation, and we are going to put first neighbor attractive interaction because this is the one that promotes a p-wave superconducting order. And once we have our mean field Hamiltonian, we are going to compute the band structure without interactions and with interactions, and also we are going to compute the Chern number just to make sure that we have a topological superconductor. And so this is what we do. And the bottom line is that when we have at the same time interactions that promote a superconducting state and a term in the Hamiltonian that quenches a singlet state, then spin triplet superconductivity may appear. And so the idea is that you start with a band structure that looks like this. So the electron part are these two red bands over here, and one band is spin up, the other band is spin down. And since you have a spin splitting in between the bands, then singlet superconductivity cannot appear, and the only superconductivity that can appear is the spin triplet. And in particular, once you add the attractive interactions, spin triplet appears naturally due to the attractive interaction, and this spin triplet in 2 dimensions give rise to a topological superconductor that has a finite Chern number, and this Chern number is -1 for this system. And this is, of course, something that can appear in systems in the presence of very large magnetic field. In particular, in certain 2D materials, when you apply a very large in-plane magnetic field, then you promote the appearance of this spin triplet superconductivity. Okay, so now let us go through the question. So the first one is, how do we know if this spin triplet superconducting state? Well, the reason is that the large exchange field effectively quenches spin singlet state, and once this spin singlet is quenched, then the only alternative is a spin triplet state. Then the next question is, what happens if we remove the exchange field? And so for this, it is useful to just copy the example and run it again. And so what we are going to do now is we are going to remove the exchange field. So we comment this line over here and see what is the superconducting state that we get. And so the idea is that if you don't have a term in the Hamiltonian that quenches spin singlet, in principle, interactions will always try to promote spin singlet. And the reason for that is because spin singlet states, they can very easily gap the whole Fermi surface. In particular, an S-wave superconducting state gaps all the Fermi surface equally. And that is, of course, energetically favorable. Whereas spin triplet states, they sometimes have more difficulties in gapping the whole Fermi surface, and so they are not so energetically favored unless there's some term in the Hamiltonian that explicitly quenches spin singlet states. And so this is the case in this triangular lattice. So if you remove the exchange field, then you see that with attractive first neighbor interactions, you do get a superconducting state, but this superconducting state is actually a spin singlet state. And then which one of the two orders is topologically non-trivial? Well, the one that was topologically non-trivial was precisely the spin triplet state, because we could see directly here from the Chern number, right? So this one has Chern number -1, and this has Chern number 0. Okay, so now we are going to look at the topological modes of this interaction-driven spin triplet superconductor. So the whole idea is that we are going to take the very same triangular lattice as before. We add our exchange field, we add our attractive interactions, we solve this problem at the mean field level. And once we have the mean field solution, we are going to look at a finite system. So we create a ribbon out of the two-dimensional Hamiltonian. We compute the bands of the ribbon. And afterwards, we are going to compute the local density of states at zero energy. That is going to tell us where the zero energy modes are located. And so the whole idea is that if we have a system that it's topologically non-trivial, in particular in this case, because we have a spin triplet topological superconducting state, then this has a very important consequence once the system is finite and when we consider a ribbon. And that consequence is that we are going to have topological edge modes that appear precisely because the gap is topologically non-trivial. And so the whole idea is that this existence of a finite Chern number is directly linked to the presence of topological edge modes. And here are the results. So you see that the band structure of the system has a gap in the bulk, right? And that you have two modes here and there that cross the gap. And in particular, if you look at the local density of states at these two energies, you see that these states are localized at the edge. So these are precisely the topological modes of the unconventional superconducting state. And since the system had Chern number 1, then we have one mode per edge. Okay, so let us now go with comparing the trivial and topological superconducting order parameters, in particular first in the bulk. So what we are going to do is we are going to take a triangular lattice, and in this triangular lattice, we are going to add a certain pairing. We are going to compute the bands and project it onto the electrons, and we are going to plot the bands. And so the first one that we see here is one superconducting order that has Chern number 0 and another one that has a Chern number -2. Particularly, the first one is S-wave and the second one is chiral P-wave. Okay, so the one important point is that the electronic structures of these two superconducting orders, they are surprisingly similar, right? So here you see that there's a gap everywhere in the Brillouin zone, there's a gap everywhere in the Brillouin zone, but the two gaps are topologically equivalent in a sense that one has Chern number 0 and the other one has Chern number -2. So the first question that we need to answer is what happens if we have simultaneously S-wave and P-wave order. So what we are going to do is we are going to compute another case, and we are going to add two types of pairing. So we are going to add one that is S-wave and another one that is chiral P-wave. And we are going to do it first with the same amplitude. And so if we add both of them, we see that we get a bigger gap, right? And now what we can do is to add different values for each one of them. So 0.2 for one, 0.1 for the other. And so in this case, you see that there's a splitting in the bands, right? So, and the reason why we have this splitting is because the two gaps are gapping the Fermi surface in different ways, which in practice means that the two gaps are acting on different parts of the bulk loop of the Jens Hamiltonian. Okay, now we are going to look at how the bulk and H spectra differ for trivial and topological superconducting orders. And in particular, we are going to take the Hamiltonian of a system that has either a trivial gap in the bulk or a topological gap in the bulk, and we are going to plot the electronic structure at the edge. So we are going to take a triangular lattice, make a ribbon, and then add a certain superconducting order in the bulk of this system. So we're going to add a superconducting order that is either S wave or chiral P wave, and we are going to see how the electronic structure looks like. And so this is what we are computing here for a certain width of our ribbon, so in particular for width 20. And this is what we see. So here you see that for S-wave superconducting gap, then there's no gap in the system. And for chiral P-wave superconducting order, there's a gap in the bulk, but then the edge has two chiral states. So one located in one edge, the other located in the other edge. And so the first question is what happens if we add both S-wave and chiral P-wave orders? So what we can do is to add a little bit of additional S-wave to both cases, right? So we are going to add S-wave over here and say that now the delta is going to be smaller, so something like half of it. And if you do that, you will see that the topological states, they remain. So even if you add a mixture between P wave and S wave order, the topological modes, they remain there. And the reason why they remain there is because they are, of course, topologically protected. So even mixture between different superconducting orders is not going to affect topological modes as long as those topological modes are protected. And then the next question is to change the chemical potential, how the electronic structure changes. So the way in which we can change the chemical potential is by adding a certain on-site energy here, right? So we can take an on-site energy of, for example, -1 instead of -3. And when we do this, we will see that the bulk spectra is going to completely change because, of course, there has been a change, but the edge modes remain. In particular, because we still have a chiral P-wave order that it's still topological. Okay, and now we are going to discuss gapped and nodal superconducting orders. So we are going to take a triangular lattice, and we are going to add first S-wave superconductivity, that it's a fully gapped superconducting order. What this means is that you get a gap everywhere in the Brillouin zone. And then we are going to consider a gap that it's nodal, meaning that it takes zero value in some places in the Brillouin zone, and in particular, we are going to take an F-wave nodal order. And with these two orders, we are going to compute the electronic structure. So you see that for the S-wave superconducting order, we get a gap in this crossing, get another gap in this crossing, but with the nodal F-wave order, there's a gap in this part of the Brillouin zone, but this band remains gapless. And so let's look at the question. So first, why does an F-wave order realize a spin triplet superconducting order? And so the reason is that F-wave is actually odd under momentum, right? So F corresponds to L equal to 3, and an L equal to 3 changes sign as you go from plus K to minus K, and therefore is odd in momentum space, which means that it's a triplet. And then the next question is, in which points of the Brillouin zone the triplet order must have nodes? And so the point is that if you have a superconducting order that is odd in momentum, it must be zero in all the points of the Brillouin zone that are their own time reversal symmetry. What this means is k equal to 0 and k equal to plus minus pi in any of the coordinates. Okay, so now we are going to move on to consider S-wave superconductivity in the presence of spin-orbit coupling. And so the bottom line is that spin-orbit coupling creates spin splittings in momentum space, but these spin splittings, they actually don't damage the S-wave's order because they happen in opposite ways in different momenta. And so the way in which we can see this is the following. So you can take first an electronic structure with spin-orbit coupling, for example, with Rashba spin-orbit coupling, that creates a momentum-dependent splitting. So different parts of momentum space get split in different ways, but what's important is that points at plus k get the opposite splitting at minus k. And then when you add a superconducting order, you still get a finite gap. So spin-orbit coupling does not damage S-wave superconductors, and in particular spin singlet superconductors. And in particular, if you change the value of the spin-orbit coupling, then the superconducting gap remains all the time. So you can take a very, very big spin-orbit coupling that makes a huge splitting in momentum space, and still your gap remains there. What this means in practice is that S-wave superconducting orders are robust to the existence of strong spin-orbit coupling. And that's why we can have superconductivity even in very big elements that have very large spin-orbit coupling effects. Okay, and then the last question is why the spin-orbit coupling does not impact superconductivity as magnetism was impacting it. And the reason is because spin-orbit coupling creates splittings, but that they are opposite at different momenta. And so in practice, superconductivity is going to couple this red band with this blue band over there. And so spin-orbit coupling is not breaking the degeneracy that allows superconductivity to appear. And in particular, spin-orbit coupling does not break Kramer's degeneracy, meaning it does not break time reversal symmetry. So in general, perturbations that do not break time reversal symmetry are not detrimental for an S-wave superconducting order. Okay, so now let us look at the combination of S-wave superconductivity with magnetism. And so what we are going to do now is we are going to take a square lattice and add both a Zeeman term and S-wave term and see how the bands look like. So the bottom line is that without a magnetic order, you have a gap, and then as you add a little bit of magnetism, your superconducting gap starts closing and closing and closing and closing. And so, of course, the bigger the superconducting term, the later this closing due to the magnetism happens, right? So if we now increase the value of the S-wave order to something like 0.5, then the value at which J closes the gap becomes bigger, right? And so the whole idea is that there's this competition between magnetism and S-wave superconductivity. If magnetism wins, then your system becomes a magnetic metal. If superconductivity wins, your system becomes, well, remains superconductor. And this is also the reason why magnetic disorder is very detrimental for a conventional superconductor. And the way in which we can see this is by taking a triangular lattice, for example, making a supercell and adding some impurities that are magnetic. And the way in which we do this is by adding some impurity in a site number 0 with a certain direction of the magnetization. And we do this for every single site for different values of the magnetic order. And so what you actually observe is that in the presence of this magnetic impurity, then in-gap states appear. So without magnetic disorder, you have a perfect gap. And then once you add magnetic disorder, you start getting in-gap states. And so this phenomena is the same phenomena that you see here, that the combination of magnetism and superconductivity closes your superconducting gap. And you can think that magnetic impurities are in a way breaking your superconductivity locally. Okay, now we are going to see how we can create an artificial topological superconductor. So for this, we are going to combine conventional S-wave superconductivity, magnetism, and strong spin-orbit coupling. So the whole idea is that we are going to start with a triangular lattice. We will add Rashba spin-orbit coupling. We will shift our chemical potential, and we are going to compute the bands in this limit. Then we are going to add a Zeeman field, and then after we are going to add superconductivity. And so the whole idea is that when you add first a Rashba spin-orbit coupling, you create this momentum-dependent splitting of your band structure. Then after adding the exchange field, you open up a gap in certain crossings. And then if you put your chemical potential over there, you cross a certain number of helical states, and crossing that number of helical states, once you add superconductivity, give rise to a topological superconducting state. So in particular, in this case, you get a topological superconducting state with chair number 3. So the first question is to decrease the value of the Rashba spin-orbit coupling. Does the splitting in momentum space become bigger or smaller? And so this is something that we can do here. So we can decrease the Rashba and say, for example, 0.5. And when we take 0.5, you see that the momentum in reciprocal space becomes, the momentum splitting in reciprocal space becomes smaller, right? So in general, the bigger the Rashba, the better. Then the next question is, why an out-of-plane field opens a gap in some of the previous crossings of the band structure? So, well, the reason is because an out-of-plane exchange field creates mixing between these two spin channels. And remember that red and blue here means the in-plane component of the spin. And then the next question is to decrease the value of the exchange field. Do the anti-crossings become bigger or smaller? So this is something that we can see very easily. So we can take a small exchange field, which is this parameter over here. So if we take, for example, 0.1, then the anti-crossing in the bands becomes smaller, right? So now this anti-crossing here is very, very small. And so, of course, to get a topological superconducting state, we want to have a large splitting. So we can put it back at 0.6. And then what happens if we change the chemical potential? And the bottom line is that the chemical potential is instrumental. So if you take a chemical potential that is not the right one, then you completely change your Chern number. And in particular, you can go to a trivial state. So in particular, with this chemical potential we had by default, we got a Chern number equal to 3. But now if we choose a different chemical potential, so for example, 0.6, we can go to a completely different state that in particular now has Chern number equal to 1, or of course, if we choose even a different value, we can go to a system that has no Chern number whatsoever. So for example, in this case, the Chern number is 0. So when engineering a topological superconductor with S-wave superconductivity, the value of the chemical potential is exceptionally important. And now we are going to see how are the edge states of this system. So we are going to take the same triangular lattice with Rashba spin-orbit coupling, certain chemical potential, some Zeeman field, and S-wave superconductivity. We create a one-dimensional ribbon. And now we are going to compute the edge states of this artificial topological superconductor. So what we do is we create a triangular lattice, we generate the Hamiltonian, we add Rashba spin-orbit coupling, we shift our chemical potential, we add a Zeeman field, superconductivity, and then we generate a one-dimensional system, so a ribbon. We compute the bands of our ribbon, and then afterwards we compute the local density of states of the system in order to see where the zero modes are located. And so the whole idea is that if you take the right values of these parameters, you create a topological superconductor with Chern number 3. So you see that you have 3 edge states over here. And so when you look at the local density of states at 0 energy, you see your states are located at the edge, as you expect from a topological superconductor. So let us go through the question. So first is the localization of the edge modes depends on the superconducting gap. Show that for boundaries yielding a small topological gap, the edge states are more delocalized. And so one way of having a small superconducting gap or topological superconducting gap is by decreasing the value of the S-wave superconductivity itself. And so if the S-wave superconductivity is very small, then you see that the gap is very small, and this is effectively what you see here. So actually, some of the states actually hybridize already a lot, right? And in particular, your system is too narrow and your width is very small, then you may not see edge states at all. So we make the system very narrow. You see that now it is not possible to distinguish what is a bulk state and what is an edge state. So in order to have well-resolved edge states, we really need to have this this system that is wide enough and a gap that is sizable so that the edges are effectively decoupled. Okay, and then the next point is that we can see that there's a gap closing as we increase the value of a certain parameter, in particular the value of the exchange field. And so this is what we are doing here. We are taking a triangular lattice, adding a certain chemical potential, a certain Rashba spin orbit coupling, but now the exchange field is going to be a parameter that we tweak, and we keep a certain S-wave superconducting order finite. So the whole idea is that if the exchange field is 0, then you have a conventional S-wave superconductor. As you increase the value of the exchange field, you start closing the superconducting gap and eventually reopening the superconducting gap.